Hello friends, Mr. Burrell here. We are just getting started into Unit 6. Unit 5 was all about simplifying, multiplying, dividing, adding, subtracting, and solving rational functions. So all these functions that are written as fractions. All these types of functions that were written as fractions. We talked about how we can solve equations that are in this rational form and how we can add, subtract, and multiply these different kinds of rational functions. So this unit, Unit 6, we're going to extend us talking about rational functions. Specifically, we're going to be talking about graphs of rational functions. We've talked about all these different equations and how we work with these different rational equations and expressions. Now we're going to move on and extend that a little bit and talk about graphing and utilizing graphs of rational functions. So this is going to be what this whole unit talks about. So what does the graph of a rational function look like? We're going to see lots of these graphs in this unit, in this lesson especially. So what do these rational functions look like? Well, here are just a few examples of what rational functions would look like on a graph. So you take a look at these. They look pretty intense. They look kind of cool. They're kind of all over the place. We're used to seeing like lines or parabolas or these nice little swervy polynomial functions. But you notice on here there's lots going on. There's like these little dotted lines. There's little circles in some places. So this is what a rational function might look like. And in the upcoming lessons we'll talk about why it is that these rational graphs look the way that they do. But I just wanted to expose you to this, get you an idea of what some of these might look like. So the question that I get asked all the time, Mr. Burrell, when are we ever going to see this? When are we ever going to use this? Well, here's just some of the examples where you see rational functions or rational graphs being used in the real world. I talked about some examples in Unit 5. I'm going to talk some other examples here. So, and some of these we'll see very specific examples of. But rational graphs and functions can be used to model the spread of a virus, so like in the healthcare area of the world. Modeling blood concentration with an injection, so lots of people in pharmaceutical companies use rational functions to determine how much of a certain drug patients can have. We can use rational graphs and functions to model bacteria growth, so it's like in some chemistry applications. Finding averages, lots of like credit card companies and banks use rational functions to determine payments and determine interest and things like that. And the list goes on and on and on. We could talk about where you're going to see rational functions all over the place, but those are some examples that you'll see rational functions being used in the real world. And we'll talk about some specific examples in some of these areas later on in this unit. So, as an introduction, before we get crazy into these different kinds of graphs, we're just going to introduce ourselves to looking at these different graphs, identifying the different critical pieces, the different critical characteristics of these rational graphs. So this is section 6.1. So by the end of this lesson, this is what I hope you're able to do. I want you to know what the domain is. We're going to define what the domain is and identify the domain of a function by looking at its graph. I want you to know what a hole is and identify a hole of a function by looking at its graph. I want you to know what an asymptote is and identify vertical and horizontal asymptotes of a function by looking at its graph. So we're going to look at some graphs, identify these different and a couple other key characteristics. And then this last objective, identifying a slant asymptote on a graph, this is going to be an honors topic, so if you want to look into that, I can explain it to you later, but I won't specifically cover it in this video. Okay, let's get into it. So if you have guided notes with you or downloaded off of our Canvas page, you can use those. These slides will cover those guided notes really, really closely. Okay, so some of these definitions. First, we're going to talk about domain. This is a word you've heard before. This is a word that you've talked about in past math classes. So the domain of a function or the domain of a graph is all the possible x values for that function, or all the numbers for x that can be used in the function. So if we were looking at a graph, the domain is all the possible x values that touch that graph. And we'll talk about that more. We'll talk about how we write that and how we see that in an actual graph. An intercept, we've talked about this in the past. An intercept is a point where the graph intercepts or touches the x-axis or the y-axis. When it touches the x-axis, we've called those solutions. Remember in the past when we talked about polynomial functions, anytime I touched or crossed the x-axis, that was a solution. So an x-intercept or a y-intercept is where I touch or intercept the x-axis or the y-axis. A hole, this might be a little bit new. Holes are something on a graph that we introduce you to when we talk about rational functions, because they start to pop up in rational functions. So a hole is a point on the graph where the function isn't defined. So in the entire domain of where this graph exists, if there's a point on the graph where that function isn't defined, that isn't in the domain, there's a hole in the graph. And we denote that with, we don't want our computer to shut down. We denote that with an open circle. And I'll show you that on the next slide. But a hole in a graph is a point on the graph where the function is not defined. An asymptote, this may or may not be a word that you've been exposed to before, but an asymptote is a line that the graph approaches or gets really close to, but never touches. So an asymptote is a line that the graph approaches, but never touches. And on the graph, it's denoted with a dotted line. And I'll show you what that looks like in just a minute. So an asymptote represents the numbers excluded from the domain because they make the function undefined. So similar to a hole is just a point on the graph where the function isn't defined. And an asymptote represents the numbers excluded from the domain because they make the function undefined. Blah, blah, blah. Lots of math terminology there. I'll show you kind of in real time what these look like in an actual graph. Okay, so on your guided notes you have this graph right here. So I'm going to use this graph of a rational function to define and kind of help you visualize each of these different characteristics, each of these different things on the graph. So, a hole on the graph, it looks like this. So on this graph, this little open circle right here, that open circle on the graph represents a hole, or a point on this graph where the domain of the function is not defined. So everywhere else on this little line is all good and well, except for this point right here. That point is not defined. And I write that with an open circle like that on the graph. It means I have a hole. How I write that, so if I'm writing without the graph what represents that hole, I write according to the x-axis. So this hole exists at x equals 3. Because at x equals 3 on this graph, there's a hole. So whenever I have a hole on the graph, it looks like an open circle, and I write it x equals whatever the x-coordinate of that hole is, in this case 3. A vertical asymptote is an asymptote, or a dotted line, that is going up and down. So you notice here, this is a vertical line. This dotted line is a vertical asymptote. So it looks like a vertical dotted line. Remember that a vertical asymptote is a line that the graph gets really close to, but it never touches. So as this graph keeps going up and down, it's going to get really close to this line, but it's never actually going to touch that line. I write this vertical asymptote, again, according to where it crosses the x-axis. So all of these x values are x equals 2. So I write my vertical asymptote as x equals 2. That's my vertical asymptote and how I write it. It's a vertical dotted line, and I write it according to the x-axis. Now, the domain is everywhere that the graph touches walking along the x-axis. So like if I was to walk from the left all the way at negative infinity here, all the way to the right at positive infinity, at which of those x values does my graph touch? Well, you'll notice that the x value of 2 here, this asymptote, I get really close to it. So walking from left to right, my domain goes from negative infinity all the way up to 2, because this graph comes and it gets really close to 2, but it never actually touches 2. So I go from negative infinity all the way to 2. And then my domain is also from 2 to 3. 3 is not in the domain. It's an open circle, so it's not included in the domain. And then my domain goes from 3 to infinity. So those values are all the values that x touches. All the possible x values for this function. That's what the domain is. All the possible x values for this function. Okay. An x-intercept is any time I cross the x-axis. So that's usually denoted, I usually denote it with like a dot or a closed circle of some sort. And I denote it by saying x equals, and in this case, x equals 1. That's where I touch the x-axis. A horizontal asymptote is a horizontal dotted line. So on the graph, it's going to look like this, right there, a horizontal asymptote. Oh, whoops, let me go back. And the way that I write a horizontal asymptote is according to the y-axis. See how it crosses the y-axis right here, this asymptote does? So my horizontal asymptote I denote by writing y equals 1, because this is the line right here, at y equals 1. Notice that the graph gets really close to that line, but it's never actually going to touch it. That's why I call it an asymptote. And then last, my y-intercept is where I touch the y-axis. So I touch the y-axis right here. Again, I usually denote that with like a little dot. And it looks like that's approximately at y equals 0.5. That's where my y-intercept is. So these are what each of these different characteristics of these rational graphs look like and how we would write them when I'm asking you to identify them. Okay? Feeling good? So let's look at some actual graphs. So this first graph right here. First, I'm going to look for any holes. And you'll notice on this graph, I don't have any open circles, so there are no holes, or not applicable. There are no holes in this graph. Vertical asymptotes. So I'm looking for dotted lines that go up and down. So let me change colors here. So right here, I have, actually I want this color. Right here, I have a vertical asymptote at x equals -3. And I have another vertical asymptote at x equals +3. So I have vertical or up and down dotted lines at x equals -3 and x equals +3. My domain is everywhere the graph touches. So in this function, it's going to be basically everywhere except for a hole or a vertical asymptote. So my domain starts at -∞, and it goes all the way up to -3, because that's where I have an asymptote. My graph doesn't actually touch that line. And then my domain also goes between -3 and 3, right in between there. And let me write this a little bit closer together. -∞ to -3, from -3 to 3, and from 3 to infinity. So basically, my domain is everything from x equals -∞ to x equals +∞, except for -3 and +3, because that's where my asymptotes are in this case. So I'd write my domain from -∞ to -3, -3 to 3, and 3 to +∞. So I have little breaks at -3 and +3. My x-intercepts. My x-intercepts, I'm looking for where I touch the x-axis. So let me change colors here. Wherever I touch the x-axis represents an x-intercept. So at x equals -2 and x equals +2 represent my x-intercepts. My horizontal asymptotes are any of my left to right, or my horizontal asymptotes, or a dotted line going from left to right, which in this case goes through y equals 1. So my horizontal asymptote is at y equals 1. Then the last thing I need to find is my y-intercept, or any place that I touch the y-axis, which in this case looks to be about y equals 0.5, halfway between 0 and 1 here. So that would be my y-intercept. So I've identified all the different parts, all these different characteristics of this rational function graph. Okay, let's look at the next one. So, on this graph right here, this middle one, is there a hole in this graph? Yes, there is, denoted with this little open circle. So, at x equals -2, because I denote the hole with the x-coordinate, at x equals -2, I have a hole. That's going to be a number that's not in the domain. That's not an x value. It doesn't work for this function. My vertical asymptotes, let me change colors again. I'm looking for a dotted line that goes up and down. So right here I have a vertical asymptote that crosses through x equals -3, so my vertical asymptote is at x equals -3. Now that I know the holes and the vertical asymptotes, let's write what the domain of this function would look like. My domain always starts all the way at the left over here at negative infinity. And my domain goes from negative infinity all the way up to negative 3. I'm never actually going to touch negative 3 on this graph because there's a vertical asymptote there. But my domain's going to be from negative 3 to negative 2. So I have the graph in between negative 3 and negative 2, and then I have a hole at negative 2. And then I also have the rest of my domain from negative 2 all the way to positive infinity. So going all the way to the right here, as I keep traveling towards the right on this graph to positive infinity, that graph will go all the way. It will keep going forever and ever and ever. So that was the domain of this function. Next, let's look at the x-intercepts, which is any place that I touch the x-axis. In this case, I touch the x-axis at x equals 2. Right here at x equals 2, I cross the x-axis. Next, let's find our horizontal asymptotes, or a dotted line that goes from left to right. Right here, this dotted line right here is a horizontal asymptote that passes through y equals negative 1. So my horizontal asymptote is y equals negative 1. And then the last thing I'll identify is my y-intercepts, or any time I cross the y-axis. That might be really close to like 0.8 or something like that, however you want to call that. So that would be my y-intercept. So done. I've identified all of these different characteristics according to this graph. You have one more graph on your guided notes. You can do this for practice as some additional practice as an additional example for you to identify these different characteristics. But that's all that I have for you for this lesson. So hopefully, after this video, you now know what the domain is of a function and how to write it, what a hole is of a function and how to write it, and what an asymptote is, both a vertical and a horizontal asymptote. Remember that this is an honors objective that if you're in regular, you won't need to worry about. But hopefully now you're able to identify these different characteristics of these rational graphs. In the upcoming lessons, we're going to start talking about a little bit more how to find these different characteristics even when the graph isn't given to you, even if we just have an equation. So something to look forward to, something to nibble on. I hope that's helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.